Welcome back to our little mini-series on the NanoVNA, this amazing instrument that you can buy for somewhere between $60 and $140. Many of us buy these and use these to measure antennas. For example, we may want to know what the input impedance of the antenna is as seen by our transmitter. So we hook up the VNA in place of the transmitter to the transmission line and look at the performance of the antenna in terms of impedance or SWR or return loss. What antennas fundamentally do is take a voltage or current excitation and turn it into propagating electric and magnetic fields. And those propagate out away from the source and eventually get over to a receiver where they induce currents in a receiving antenna, which is fed to an amplifier and filters and all of the other radio electronics. Well, in addition to measuring the performance of the antennas used, as we've seen in a previous video, you can use the NanoVNA to measure an entire amplifier and check the gain of the amplifier and its frequency response. And this is the amplifier that we did that in a previous video. But when you're designing the amplifier, people who design RF electronics have to understand what are called parasitics. The problem is magnetic and electric fields are not just things that we radiate out into space. They exist around all components that have voltages across them or currents flowing through them. That means that, well, let's take this inductor for example. This inductor we hope is an inductor, but as we're going to find out in this video, this inductor at a high enough frequency turns out to be a capacitor. And in addition to that, you probably won't be surprised that there's some resistance in the wires here. And at very high frequencies, that resistance can become more substantial than we think due to skin effect. And when you design an amplifier, you have to put the inductor in, you have to know the basics of it, but you also have to know the performance limitations of your components. That's what we're going to talk about today. On this particular board, in addition to the amplifier, which is up here at the top, there's a test structure, and there's a little test connector here. And that test connector is a UFL connector, just like on this RF demo board that contains the short, open, and load calibration structures and some of the other example component structures that we looked at in a previous video. What I've got here is the VNA already calibrated. It's hooked up to the short structure so that we can check the calibration, and as it should be, it's showing over here on the left side of the Smith chart. It's reading out as 64 milliohms, 62 milliohms, whatever, in series with about 5 nanofarads. So that's not bad. Now, in this video, we're going to sometimes, instead of reading the ohms and the equivalent capacitance, we can go to marker and Smith value and change it to R plus JX. And now you can see that it's changed to reading 60-something milliohms minus J68. That's the impedance of the capacitor. We're going to review that. More importantly, we're going to review capacitance and inductance and resistance at a basic physics level. Again, without math, but we're going to review all of that here next. Now please stay with us. I promise this is going to get interesting very soon as we test circuit elements with the vector network analyzer. But before we do that, in order to understand what's going on and what we're going to be seeing, I think it's important to very briefly review things like resistance and capacitance and inductance. So a resistor in general, from a physics point of view or a structural point of view, is a hunk of semiconducting material, often carbon, maybe some kind of a cermet, metal, ceramic alloy. You take that material and you form it in such a way that when you put a voltage across it, it impedes the flow of current. And so you have some current flowing through here, but the resistance determines how much. The equation, of course, is V equals IR, or that can be turned around to I, the current, equals V divided by R. So the higher the resistance, the less current. Everybody knows this. So structurally, we have different ways to make resistors. This is the old style leaded resistor, and this is a new style surface mount resistor. Now, this is the ideal behavior. At high frequencies, at radio frequencies, these leaded resistors can become real problems, as we'll see. That's one of the reasons that we went to surface mount, although another one was to reduce the size of the electronics. To understand, however, that even the surface mount ones have some limitations, we need to look at capacitance and inductance and then come back to the resistor. So here's the capacitance case. And I wrote capacitance rather than capacitor because capacitance occurs everywhere in the real world. Anytime you have two conductors, here's one and here's one, that are close to each other, there's capacitance between them. If you put a voltage on them over here, current will flow into one side and put positive charge there, and the other side, negative charge, will be induced, and there will be electric fields between them. It doesn't matter whether they're plates on a capacitor or they're just two pieces of metal of any shape near each other. Now, of course, for continued current flow, we need to have an AC source, and that's why I've used an AC source over here instead of a DC source. In that case, we end up talking about the impedance of the capacitor. And we have the same Ohm's law relation, V equals I times Z instead of V equals I times R. Z is a function of the capacitance, but also a frequency. So it's 1 over 2 pi FC. That's actually the reactance. Z, the total impedance, has a J down here in the denominator. All that means is the current and voltage are 90 degrees out of phase with each other. The capacitance itself is a function of how big the stuff is, and what's the separation distance between it, and what's the permittivity of the material that separates them. Lastly, before we go back to the resistor, and the real issue today of parasitics and radio design, because you have to know how parasitics exist in order to design a successful product, let's look at inductance. Inductance is oftentimes a coil of wire, but here I've just drawn it as a wire to emphasize the fact that just like capacitance, inductance is everywhere. So if you put an AC source, in this case, on this wire here, you're shorting out these two terminals. In DC, that would be really bad because you'd have super high currents. But in AC, what happens is as current starts to flow through here, a magnetic field builds up, and that changing magnetic field induces what's called the back EMF and opposes the voltage applied. And so as this evolves over a full cycle or many cycles, what we find is there's a finite amount of current, and it's related to the impedance of the inductor. And the impedance of the inductor is 2 pi FL. So the higher the frequency for a given inductance, the higher the frequency, the higher the impedance. Again, the J is something that captures mathematically the 90-degree phase relationships involved. We're not going to get into that today. One last thing, the inductance is the total flux created by the current flowing through the wire in this case, or in general through a loop here. And so what's flux? It's magnetic field B times the area in which it's flowing, and so you have kind of this area that the B field flows through. There's integrals involved and all that, but in essence it's really just the bigger the area, the more inductance you're going to have. So now let's talk about resistors at radio frequencies, and let's measure it with the NanoVNA. Here I have a 22 ohm resistor, and one side is attached to the center pin of this UFL connector. UFL connector ground goes to the back side of this board, which is a copper ground plane, and then the other side of the resistor goes through a via hole to that backside ground plane. So we're going to measure this, and what you're going to see is that this is not just a 22 ohm resistor once you get above, say, 100 megahertz. Why? Because there's wires here, and there's an area here, and you're going to get magnetic fields and back EMF, and you're going to induce inductance. And here's what the NanoVNA does for us. It allows us to understand the performance of something like this resistor, which has these leads on it, at radio frequencies. In this case, I've got the marker set at 100 megahertz. The readout says it's 22 ohms, but there's a 21 nanohenry series inductance involved with that. So the point is not down here where it should be. Instead, it's up here because we have some added series inductance, as we now expect. At a somewhat higher frequency, I've moved it up to 390 megahertz so that I'm on this J50 arc. It's still reading 22 in series with 20 nanohenries, but because we're at a higher frequency, the inductive reactance is now 50 ohms. As we can see here, now that I've reset the Smith value readout to be R plus JX, we can see that it's 22 ohms resistive in series with 49.6, which rounds to 50 ohms of reactance. So it's not a 22 ohm resistor at radio frequencies. This is only 390 megahertz. I mean, that's like the 440 band or the 70 centimeter band, or not even there. So resistors, you have to watch out for them at radio frequencies. The simple solution is to not do this. Never have a resistor sticking up like this. Always mount it as close to the board as you can. However, even when you do that, the resistor has a length and current's flowing through that length, and you're going to get some series inductance. So the real solution is to use very small components, surface mount. And here's an example to show that. This is using the RF demo board, and the readout is now right here. This is a 33 ohm resistor. I don't have a 22 on this demo board. It's a 33 ohm resistor, but we do not have the arc that we had before. We don't have the series inductance. There's a itsy bitsy tiny amount of series reactance here, 0.29, 290 something milliohms of reactance, but compared to 33 ohms, that's insignificant. So it's basically a good 33 ohm resistor because it's surface mount. So to summarize what we've just seen, this is a handout from a radio class, and it shows component parasitics at radio frequencies. Here's the leaded resistor, or drawing of one. Here's a drawing of the surface mount one. Here's the ideal model. This is what we want to believe, that the resistor just behaves the way it does in a schematic. But in reality, at radio frequencies, the model at RF is the resistor in series with some inductance. And we haven't talked about the capacitance yet, but there's some conductors here, and they're near each other. So whether it's this form or this form, there's capacitance from end to end. And if there's a ground plane below the resistor, there may be capacitance down to that ground plane, which is shown here. The bulk of the issue, especially for low value resistors, is captured by this series inductor, which is added to the model. So when you're analyzing the circuit or simulating it, you need to be putting in realistic models for the inductances of your resistors if you don't know in advance that you're not going to have a problem. Now, the 33 ohm resistor, it didn't have any significant series inductance, so we don't have to get all fancy. We can simulate, we can design using just this. But the leaded resistor, not so much. And with the surface mount one, if we get into the gigahertz range, some of this inductance may matter at that point. Now, if it's a 1K ohm resistor, and if the capacitance that we mentioned is significant, then at very high frequencies, it can roll off in the total impedance. And here's an example of that high resistance case. This is a 9100 ohm resistor, 9100 ohms. What it's reading out as is 260 something ohms in series with 0.12 picofarads, or 120 something femtofarads. Now this is a little bit more complicated because the model that we had a resistance in parallel with some capacitance, and this is a series impedance readout, or in this case series resistance, and the effective series capacitance. If you do the conversions, which I did a minute ago, it comes out to 7,235 ohms. But that's in parallel with about 1.2 k ohms of reactance. And so the net impedance is lower than either one of those two values. So for the 9100 ohm resistor, the total impedance is much less than 9100 ohms. It's somewhere around 1 k ohms. So what's the bottom line? Are resistors worthless at radio frequencies? No, not at all. However, depending on the dimensions of the devices and the frequencies involved, you may have to limit yourself to using resistors from, say, 10 ohms up to a k ohm or something like that. If you've got surface mount parts, might not be a problem to go much higher than that and much lower than that. But you can't have arbitrary values. You can't get 0 ohms at radio frequencies. You can't get infinity ohms at radio frequencies. There's always capacitance and inductance working against you. So let's move on to capacitors and see if we can understand the parasitics involved there. We've got all the groundwork. We can go through this much faster now. So a capacitor might be a disk capacitor like this with some leads, or again, it might be a surface mount capacitor. The ideal model, the one we want to use when we're thinking about it, designing or simulating, looks like this. But as we know, depending on the dimensions and the frequencies involved, we have inductance. There's always inductance, and there may be some added capacitance. We'll assume that's taken care of in the capacitor itself. But the inductance can bite us. And here's the model. Because of the leads, or because of the simple dimensions of this capacitor, or more likely because this capacitor is soldered on a board that has some traces that look like this and they go somewhere else on the board, you're going to have some lead length, which is basically the traces on the circuit board. So you've got to account for that too. It's not just the capacitor that matters. It's the whole circuitry that you're designing, the physical circuit. What's the behavior? Well, at low frequencies, it acts as a capacitor. No problem. So at low frequencies, it goes up as the frequency goes down. But you now have an inductance in series with a capacitance, and you may recognize that as a series resonant circuit. And a series resonant LC circuit tends towards zero impedance at the resonant frequency. That's shown here, but it's not shown as completely 0 ohms because there is some power loss in this capacitor which manifests itself as some resistance, and there may be some resistance in the traces or the capacitor itself or the dielectric materials. In any case, it dips to a minimum at some frequency and then it goes up. So to investigate this issue with a NanoVNA, you'll need a test fixture, something like this, or however you want to construct it. Make sure you calibrate to that test structure and make sure it looks like a good open when the component's not there. Here I've put in the component. It was already calibrated as shown before, and I'm using a 33 picofarad capacitor. On the Smith chart, at whatever frequency this is, 30 something megahertz, it's showing as minus something milliohms, so minus half an ohm, in series with 32 picofarads. Now, this minus half an ohm is like 0. It's also just an indication that the network analyzer is not perfect. It goes slightly outside of the Smith chart here, and that's where that minus sign comes from. So we're going to ignore that for a second, or we're going to ignore it, period, and just concentrate on the fact that it's 32 picofarads at 30 something megahertz. Now, if I go up in frequency, it will move along this arc, as it should, because capacitance is down here on the bottom of the Smith chart, but then it gets over to here, and that's the series resonant point. So I'm going to move the marker over there and let's see what the value is. All right, so over here, I've now moved into the picohenry zone, so the thing is starting to become inductive, but it's essentially nothing. It's just resistive, but it's about 0.2 ohms. Give or take a little bit. We're not quite sure how accurate the network analyzer is. They tend to be pretty decent, so we're somewhere between 100 milliohms, 0.1 ohms, and 300 milliohms, 0.3 ohms. It says 0.2, so we'll call it that. Notice, though, that as we go higher in frequency, it would move up into here, we would have much more inductance and more resistance as well. The important frequency, called the self-resonant frequency, in this case is 270 megahertz or 271 megahertz. That's for this 33 picofarad capacitor with these leads on it. Now a 33 picofarad that surface mount would not self-resonate at 270 megahertz. You'd probably be able to get to a gigahertz or more. If and only if you're talking about the impedance from this side of the capacitor to this side of the capacitor. Once you add some lamb patterns and some traces and maybe a via to the backside ground plane, this 33 picofarad capacitor may not go above a gigahertz even if it's surface mount. But that's the thing that your NanoVNA can help you understand and figure out for your own designs. Inductors. Structure looks like this. The model for a schematic, we may draw it like this. But the model at RF is very complicated. There is some series inductance involved, but since it's an inductor, we can forgive that. The trouble is there's parallel capacitance as well and resistances. Now this model is quite involved. I'm not going to get into it deeply, but you could look at this and kind of understand the capacitance. You've got a turn here and a turn here, and they're right next to each other. Remember, any metals that are near each other create capacitance. So there's like capacitance between here, and then between here, and so forth. And so there's capacitance across each one of these turns, like this. And it turns out that if you analyze it, you can kind of lump it all together into this form. The important issues are, what is the self-resonant frequency? How does it behave at low frequencies and high frequencies? And that's captured in this graph right here. At low frequencies, depending on the wire and how many turns, you could have substantial resistance even at DC. Now these would not, and so this would kind of come on down just like the ideal curve. As you go up in frequency, however, you're going to get the effects of parallel resonance. And that's going to shoot the impedance up, not to infinity because there's some losses involved. And so it's just going to shoot up to some high value. And then it's going to start coming down because as you go above the self-resonant frequency, the inductor is going to behave just as a capacitor. Because this impedance is going to be going up, this impedance is going to be going down. Whenever you have two things in parallel, the small guy wins. So it's going to go down, and above the self-resonant frequency, the inductor is pretty worthless as an inductor. It's not an inductor, it's a capacitor. But that's where the NanoVNA comes in to save the day. In this RF amp design, which is intended to work in the FM broadcast band around 100 megahertz, I needed an inductor of 150 nanohenries, so I wound one and I put it on the test jig here and measured it, and it came out to be, what does this say, 86 nanohenries. So it was not high enough, so then I got some smaller wire and wound that, and I got one that was about what I needed. And then I just stretched it out to make it exactly 150 nanohenries. Now, the other thing that's really cool about the network analyzer is you can measure what's called the quality factor of the inductor. And this NanoVNA gives you that ability. This thing, I've used network analyzers in the labs that cost $40,000, and this thing, frankly, it performs for all of the applications I've been showing here just as well as those do. There are some limitations. In particular, this only goes up to a gigahertz, but if you're working in that frequency range, these things are stunning. Now, if you've been looking closely and you're familiar with Smith charts, you may recognize that this particular inductor never hit the self-resonant frequency. Even at a gigahertz, which is the upper range of my sweep, it did not go past the infinity point here, or the high impedance point, and turn into the capacitance region. However, let's look at one on the demo board and see if we can find one that does go past the self-resonant frequency point. Here's an example of that. This is the inductor that they give you on at least the RF demo kit that I bought. And it's supposed to be like this on the Smith chart. And it would be if we were sweeping over a different frequency range. Instead of going from 1 megahertz to 1 gigahertz, if we went from 1 megahertz to, say, 30 megahertz, it might look like this. But because we're going to 1 gigahertz, two things happen. Number one, we do hit the self-resonant frequency, and then beyond that, it looks capacitive, as shown in our model. However, it also has this weird line here. That's just because this is 1 megahertz, and this is 2 megahertz over here, and then we go on up. And so there were no points taken between 1 and 2, and it simply, in the software inside the unit, drew a straight line. To read out the value with the NanoVNA, you need to set the Smith value to read R plus L or C. I've done that. You also need to run to the lowest frequency so that you're over on this side of the Smith chart. You don't want to be over here. And so I've done that at 1 megahertz, and it's reading 5.4 microhenries. So that's the base inductance of this thing. Now let's look for the self-resonant frequency. So I've moved the marker over to here, and it's reading out 2.6 k ohms in series with 2.1 microhenries. If I go to the next higher frequency, currently we're at 61 megahertz. Now we're at 71, and now it's reading 2.8 k in series with 67 picofarads. So we've crossed the self-resonant frequency point in the parallel configuration, and if we go up higher, it'll just act as a capacitor. One of the important things is we have 2.8 k ohms at the self-resonant frequency point. So that's this point right up here. And it does not go to infinity as it would if it was a perfect resonant circuit. So what we've learned is R big here could be 2.8 k ohms in this model. There's also a relationship between that resistance and the reactance of the inductor at that frequency that can give you the Q, the quality factor. Again, look that up on Google. Or in the next video, we might cover the design of this amplifier and talk about that quality factor and how it affected this design. To wrap up our discussion of component parasitics and measurement of these things with the NanoVNA, we need to consider the PC board trace, because it's not just components. There's interconnect between the components that you need to consider when you're making a radio frequency design. Absolutely critical. These boards that we've been talking about have components on one side, but like all good RF designs, they have what's called a ground plane on the other side. And that helps confine the electric and the magnetic fields and keep things under better control. In what sense is it under better control? Well, number one, if there's a ground plane right underneath this trace, then the electric field lines are going to tend to go from the trace down to that ground plane and not reach out and touch other components nearby as much. In addition to that, magnetic fields that wrap around this trace will be somewhat confined under that trace as well. But equally important, especially at microwave frequencies, gigahertz range and above, the traces that you put on the circuit board are not just connections. As we know, if there's any current flowing through them, they have inductance. There's also capacitance between that trace and the backside ground plane that we just discussed. And so the model ends up looking like this. And if you've seen some of our previous videos, you know that this is the model also for a coax transmission line. And this issue of simple circuit board traces morphing into transmission lines, these complicated LC structures that were hard to deal with because of parasitics, this issue is what created the first vector network analyzer, or spawned the first vector network analyzer, done by Hewlett-Packard, I think in the early 1960s. It also created the dawn of using these so-called S parameters. Deep, deep topic, not going to go into that in detail, but you're already learning some about the network analyzer that you have, the NanoVNA. You know it's just as good as the other VNA, and you can use it to learn a lot about radio frequency electronics. So I think I'm going to leave it here. Hope you enjoyed the video. And not sure what the next one will be. Might talk about that circuit that we showed a few minutes ago, or might go into some S parameters more. Anyway, have a good day. Thanks.